And yet again, I made the same mistake I did a couple of videos back. I clicked the button that stopped the recording altogether. So now this video is gonna be in 2 parts. That's just great. I can't record a long video because I always mess up. So before in the previous video, we showed our original sum, which again, I'll just rewrite here, just a quick recap, is the sum n is going from 0 to infinity of -1 to the n over n plus 2. Another sum, k is equal to 0 to the floor of n over 2. We have negative n minus 2k factorial, 2k plus 1 factorial, and then -1 to the k up top. So this was our main sum for last video and also for this video as well. But last video we started on showing that it can be rewritten as a sum of the form en comma k of, which is equal to a n b k c of n plus k and d of 2k plus n, and these are your number sequences on this corner. So I'm just gonna erase this. So again, I made a mistake, terribly sorry, but well, what can I do, man? So basically what we're gonna do next is, I noticed that the d subscript is a bit challenging. So what I thought about was, how can I rearrange these terms such that d wouldn't be as big of a problem as I thought before. And so here's how I thought about it. So I thought about the case where 2k plus n is equal to 0. Alright? So that's the case where this thing is equal to 0. And so we have either k equals to 0 and n equals to 0 in our interval that we showed before. And then next I thought about, what if 2k plus n is equal to 1? In which case k is going to be equal to 0 and n is going to be equal to 1. Okay, and then so I went on, so 2k plus n is equal to 2. And my conclusion was there were 2 solutions, either k equals 0 and n equals to 1, or k equals to 1 and n equals to 0. And then, n equals to 2 in this case, sorry. And then I went on again. So 2k plus n is equal to 3. And I'm actually going to write down the number of solutions it has. So we have 1, 1, and then we have a 2. Now for the 3 case, we have k equals to 0 and n is equal to 3. And we can also have k equals to 1 and n is equal to 1. So we have two solutions for this one as well. And then we're going to move on to 4 case. The 4th case, 2k plus n is equal to 4. In which case either k equals to 0, in which case n is equal to 4, or k is equal to 1 and n is equal to 2, or k equals to 0, k equals to 2 and n is equal to 0. And in which case this has 3 solutions. And you can go on and you find that the amount of solutions is going to look something like the floor of m over 2 plus 1. And here the amount of solutions to that is 2k plus n is equal to n. So basically what we've shown here is that the amount of solutions for this specific equation is this. And this is going to be useful in a way that I'll rewrite later on, but on the next blackboard, of course. And so this is what we have last blackboard. So we know that now that this equation has this many solutions for this thing, and here is just saying it's a non-negative integer. Now what we're going to do is we're going to look at this series right here without the expanded terms. And we're going to see that it is equal to e 0, 0 plus e 1, 0 plus e 2, 0, and then goes on forever. And then plus e 0, 1. And then plus e 1, 1. And then plus e of 2, 1. And then goes on forever, and this goes on forever as well. So that's basically what it means to have a double sum like this. Now, what we can tell is that for these 2 cases, this must be satisfied. Clearly, 2k plus n is always going to be equal to some number m, where m has to be greater than or equal to 0. And so here we can now rewrite this as e for 2k plus n is equal to 0, and then plus e 2k plus n is equal to 1, and then plus e 2k plus 1 is equal to 2, and then plus all the way down. And now what we can do is we can now substitute the solutions we found on the previous blackboard in for these subscripts right here. So basically what that means is we're going to have on the first row is just going to be e0, 0, which is the solution where m is equal to 0. And then here on the second row, I'm going to then plus e10, 0, which is the solution for m equals to 1. And then we're going to add e20, 0, but this time we're going to add e01. Right? And then we can continue like this. So we can add e30 plus e11, and then that's it. And then we can then add e of 4, 0 plus e of 2, 1 plus e of 0, 2. And we can go on like this. And you can very clearly see that, we get every single n and k for here, because in the first column, the k's are all equal to 0, and n starts from 0 and goes on to infinity. And then for the second column, k equals to 1, and then it goes on to infinity, and so on to the right. So we now know that these two are equal, but how do we use this? Well, if you look at this case, we can notice that, and especially if we look at this row right here, the k values, they increase by 1 each time, which we can express using standard summation notation. And then for every sort of k increase, n decreases by twice that. So basically what I mean is, like, here k is increasing by 1, and then here the n is decreasing by 2, and clearly this ends as n is either 1 or 0, and this row has this many terms in it. So how we're going to express this is, well, first of all, I'm going to go back to the bad, I say that with quotation marks, notation, and now we're going to find an interesting pattern, because here it is now equal to a naught, b naught, c naught, d naught, alright, that's the first row, plus a1, b naught, c1, d1, and then plus a2, b naught, c2, d2, plus the a naught, b1, c1, d2, and then I'm going to then go to the third row, and I'm going to stop at the 1, 2, 3, 4, 5, 5th row, just so it doesn't take up too much space. I'm going to think for a second, and then adding a2, b1, c3, d4, plus a naught, b2, c2, d4. And then now naturally this thing goes on forever as well. And now for every row, we can now factor out dn for the nth row. So for example, if we're going to go to the nth row, it would look like an, b naught, cn, and then dn, and then it's going to be applied plus a n minus 2, b1, c, n minus 1, dn, and on for this many terms, which is certainly a bit to comprehend. But now, once we've factored it out, we have now changed the rest of this, into a finite sum, which is really easy to integrate. Just sum up, to put in summation notation. And how we're going to do that? We're going to realize that this goes on for this many terms, and it should, in theory, stop at the floor of n over 2. And that's the idea. But I feel like I've already used too much space, so I'll put down my idea in the next blackboard, and hopefully I don't press the wrong button again. And this is my idea. This is what it looks like. It's gonna take some explaining, first of all. So before we knew to factor out a dn, and basically what this first sum is doing is that the n here is the index of, or the subscript of that d sequence here, and the d sequence is the 2k plus n thing. And then we have this sum right here, and you can check that this thing has this many terms in it, and that's exactly what we want. And then now what I've done is I've realized that the first term in our sort of mini-series is just an, b0, cn. And it is the same thing with this layout over here. But now, for every increase in the b subscript, we have a decrease for 2 times that increase in the a subscript, which is exactly what we saw in the previous one. And then this c here is just the sum of those two, so it's n minus k. So this is my proposal. And to be honest, when I first figured this out, it was genuinely quite the celebration. And I really wish to really generalize it instead of 2k to some other integer mk plus n. But perhaps that's a video for another day. And now, all that's left is really to just plug in our sequences. I mean, it's simple and easy as that once you've got through the, long addition backboard we did last time. And what we get at the end. You find that this series right here is our desired series in the, first video. It's weird to say first video, because I literally recorded that like two minutes ago, and then I just pressed the wrong button, and now I have to upload 2. What? And so now we have n over 2, the 4 of that, and then we're going to just plug in everything else. So we have n minus 2k factorial. I have 2k plus 1 factorial. And here we have this negative 1 to the n minus k. Now, what we can actually do is we can just multiply by negative 1 to the 2k here. And the reason why is because, you can write this as this negative 1 squared to the k. And this part is going to be 1. So that's always going to be 1. So this stays the exact same. But you can also use the property of exponents. And you can turn this negative k to a plus k. And now what we can do is we can use properties of exponents again, where we shape that again to negative 1 to the n, k to negative 1 to the k. And then now this term is independent of k, so we can then drag that out of the k sum, or mini-series, to the outside. And what do you know? This was exactly the series that we started with. To be honest, the thing with solving math problems, especially with something like this, is once everything just starts to fit together like a nice puzzle piece, it's really satisfying. And a quick recap to the beginning of the last video, which I literally recorded 2 minutes ago. The conclusion was that this series right here is equal to a specific kind of integral that we use, which is from 0 to 1, e to the negative t times the sine of t dt. And we also proved that this is equal to 1 over e times the square root of 2 times the cosine of 4 minus pi over pi, over 4 minus 1/2. And this is our final result. This rather intimidating looking sum, taking 2 entire videos, comes out to this thing with e root 2 and the cosine of some strange value. Would you look at that? And we even used a lot of Blackboard space to do it. I'll say that was a successful video. Thanks for watching.